The classification task could be solved using traditional statistical modeling methodologies. However, statistical modeling suffers from some limitations. For example, linear and quadratic discriminant analysis are not estimable when the number of predictors exceeds the sample size. There are other machine learning methods such as k-nearest neighbors and kernel discriminant analysis, but neither handles datasets that include categorical variables. Also, they give little usable information about the structure of the data, such as which variables are most important to the predictive process. Because random forests are rooted in classification trees and bootstrap aggregation, I will first discuss those methods and then describe random forests. Classification trees were developed in 1984 to handle problems that could not be handled in an easy or natural way. Classification trees are a systematic method for predicting the class of an observation given a set of covariates. Generally, the covariates associated with the observation in the training set are recursively split into two subsets based on optimal cut points that are identified by a greedy search procedure performed over all predictors. When applying a classification tree, all observations start together in what we call the root node. Then the classification tree is constructed by splitting a node into two descendant nodes. Descendant nodes are further split into two subsets. Therefore, the algorithm involves repeated splits of a node into two descendant nodes. The entire tree construction process involves a set of binary questions where each question is of the form, is X an element of A? A goodness of split criterion that can be evaluated for any split of any node. The goodness of split criterion is often reformulated as a non-negative impurity function. We also need a stop splitting rule and a rule for assigning the predicted class for each terminal node. As you may guess, the predicted class for each terminal node is taken to be the class for which the posterior probability is the largest. For the first task, we have to identify how splits of the predictor are selected. Because the tree consists of nodes, where each node is divided into two descendant nodes, we form a set of binary questions that comprise the candidate set of splits. Therefore, each binary question is of the form, is X an element of A? And we identify all possible binary questions associated with our training set. For ordered and continuous variable, this question takes the form, is X less than C? Then the associated split sends all observations in that node that answer yes to the left descendant node and all observations that answer no to the right descendant node. This ideogram demonstrates all observations starting together in what we call the root node. Observations in class 1 appear in red. Observations in class 2 appear in blue. We ask a binary question, which, for a continuous variable, is of the form, is X less than C? All observations answering yes go to the left descendant node, while all other observations go to the right descendant node. The goal is that the descendant nodes are more homogeneous with respect to class than the parent node. Notice that a split depends on only the value of a single predictor. Again, the standardized set of questions is defined such that each split depends on the value of only a single predictor. For all ordered and continuous predictors, we ask the question, is X less than C? For all possible cut point C. That is, if there are n unique values of X, there will be n-1 cut points examined for that variable. For categorical predictors taking on J levels, all questions of the form, is X a member of A, where A is a subset of the J levels, is asked for all possible subsets. Taken together, these constitute our set of questions for the P predictors. Therefore, this is a greedy search procedure, but it is computationally tractable problem because there are not an infinite number of possible splits. For the heart disease data frame, there are 462 subjects, and the outcome is whether or not the subject has coronary heart disease, which is 1 if they have CHD and 0 if they do not have CHD. There are 9 predictor variables, most of which are continuous. Each continuous predictor would be sorted, and the unique sorted values would identify all possible questions. For systolic blood pressure, we would look at all possible cut points. For example, less than or equal to 101 versus all others, less than or equal to 102 versus all others, less than or equal to 103 versus all others, etc. Similarly, for age, we would look at all possible cut points. Less than or equal to 15 versus all others. Less than or equal to 16 versus all others. Less than or equal to 17 versus all others. The only categorical predictor is family history, which is binary, so there is only one question in our set. Given that we have looked at all possible splits for every predictor, we now need to decide which predictor and split of that predictor is best. Define the node proportions in node T to be the proportion of observations in node T belonging to a class K, so that the sum of the node proportions over all K classes is 1. An impurity function is defined on the set of all node proportions with the properties that the node impurity is largest when all classes are equally mixed together and smallest when the node contains only one class. Symbolically, the impurity function should have this form, which simply indicates the impurity is largest when all classes are equally mixed together and smallest, or 0, when the node contains only one class. Two common impurity functions that are used are the Gini criterion, which is the default in most classification tree programs, defined using this equation, and the information or entropy criterion, defined using this equation. Again, the impurity function should be largest when all classes are equally mixed together and smallest, or 0, when the node contains only one class. So while there are different impurity functions, they tend to yield similar results because their shape is the same. In order for the decrease in node impurity to be greater than or equal to 0, the impurity function must be concave. For any node T, suppose there is a candidate split S of the node which divides it into left and right descendant nodes, such that a proportion P sub L of the observations in T go into the left descendant node, and a proportion of observation P sub R go into the right descendant node. Then the goodness of split is defined to be the decrease in impurity defined by this equation. At each node, the tree algorithm searches through the predictors one by one, beginning with x sub 1 and continuing through x sub p. For each predictor, it finds the best split. Then, among all of the p best single variable splits, the best split is selected. That is, it identifies that split which gives the largest decrease in node impurity among the p best splits. This procedure is then carried out on the descendant nodes separately. The R package rpart includes a function called rpart, which stands for recursive partitioning. The rpart function accepts a model formula, the data frame name, and method, along with other parameters. Here, CHD is modeled by all other variables in the Hart data frame. Here we have indicated that we want rpart to derive a classification tree. If method is missing, the rpart function makes an informed guess at what method should be used, where the information is provided by the class of the response variable. That is, because CHD was stored as a 0-1 numeric variable, rpart identifies that the response CHD is numeric and fits a regression tree if method is not specified. If CHD is stored as a factor, rpart will correctly interpret that a classification tree should be fit even if the method argument is missing. It is good practice to specify the method you want in your rpart function call. For the heart disease dataset, this is the resulting classification tree for predicting CHD. All observations started in the root node. Then subjects with age less than 50.5 went to the left descendant node, while all others went to the right descendant node. On the right, subjects with a family history equal to absent went to the left descendant node, while all other observations in the node went to the right. Considering the left descendant node, those who used tobacco less than 7.6 years went to the left descendant node, with the remaining going to the right. Therefore, suppose we had a new subject who is 60 years old with no family history, who never used tobacco, so tobacco is 0. They would be predicted to be CHD equals 0, or to not have CHD. The initial heuristic rule was as follows. When for a node T there was no significant decrease in impurity, then T was not split and became a terminal node. That is, the initial stopping rule was simple and unsatisfactory and can be described as set a threshold to some value greater than 0 and declare a node to be terminal if its decrease in node impurity using the best split is less than the threshold. This method was noted to give dishonest results. That is, suppose the threshold was set so low so that every terminal node contained only one data point. Then the posterior probabilities would all be either 0 or 1, and the resubstitution error rate of the tree using the data would be 0. You would conclude that in general, the resubstitution error decreases with tree size. That is, when increasing the number of terminal nodes. So the more you split, the better you do. In fact, if the tree is built using a learning set and the error rate is estimated using an independent test set, it was noticed that the resubstitution error estimate becomes increasingly less accurate as the trees grow larger and larger. The test error estimates indicate that as the tree initially decreases in size, the true misclassification rate decreases. Then it hits a minimum, then begins to climb again as the trees get too small. This is a characteristic of tree growing, since it reflects the trade-offs between bias and variance. Instead of attempting to stop the splitting at the right set of terminal nodes, continue splitting until all terminal nodes are either homogeneous with respect to class, or there are too few observations for further splitting, such as setting a threshold of 10 observations or 5% of the total sample to be in a terminal node. This results in a large tree. Then, selectively prune this large tree upward, getting a decreasing sequence of trees. The two essential ingredients to this procedure are, first, prune instead of stopping. Grow a tree that is much too large and prune it upwards in the right way until you finally cut back to the root node. Second, use more accurate estimates of error to select the right size tree from among the pruned subtrees. The 1SE rule for selecting the right size tree is as follows. Define an overly large tree, then select the tree such that its error is less than or equal to the overly large tree plus 1 standard error. Here we have grown an overly large tree by specifying that each terminal node can have only 5 observations. The plot CP function provides a visual representation of the cross-validation results from an R-part fitted object against the complexity parameter CP. A good choice of CP for pruning is the leftmost value for which the mean lies below the horizontal line. Notice that this is at CP equals 0.4, which would result in a tree with 4 terminal nodes. The print CP function prints a table of the optimal prunings based on the complexity parameter. This includes the mean and standard deviations of the errors in the cross-validated predictions. Using the 1 standard error rule, the minimum cross-validation error is 0.75. Adding its standard error yields 0.808. Therefore, pruning using some complexity value between 0.025 and 0.0625 would yield the same final tree. We chose to use 0.04 as the complexity parameter for pruning our tree, as that value was indicated by the graphic and is also in the range using the 1 standard error rule. The final classification tree has 4 terminal nodes. Task 4 is a rule for assigning every terminal node T to a class. Thus, all observations in the same terminal node have the same predicted class. The tree is used as a classifier in the obvious way. For a new observation, its predictor values are dropped down the tree until a terminal node is reached. The predicted class is taken to be the predicted class for that terminal node. Advantages of tree-based classifiers include it can be applied to any data structure through the appropriate formation of a set of questions. It handles both ordered and categorical predictors in a natural way. The final classification has a simple form which can be compactly stored and efficiently classifies new observations. In other words, classification trees are easy to interpret and simple to apply. It makes powerful use of conditional information in handling non-homogeneous relationships. It does automatic stepwise variable selection and complexity reduction. Classification trees are efficient for large data sets. Classification trees give, with no additional effort, not only a classification, but an estimate of the misclassification probability for the object. In a standard data structure, it is invariant under all monotone transformations of individual ordered variables. It is extremely robust with respect to outliers and misclassified points. The tree procedure output gives easily understood and interpreted information regarding the predictive structure of the data. However, classification trees have high error rates, and classification trees are characterized to be unstable learners. That is, classification trees are sensitive to small changes in the data. A weak learner is a prediction function that has low bias, that is, on average it is correct. Generally, low bias comes at the cost of high variance. If perturbing the learning set can cause significant changes in the predictor constructed, then averaging many weak learners can improve accuracy. In fact, when averaging two uncorrelated, unbiased predictors that have the same variance, the expected value is unbiased, but the variance is reduced. The concept of averaging weak learners was first introduced as the bootstrap aggregation method. Let's start with an example. Suppose x is a random variable and y is a function of x, but includes random error as well. Specifically, y is related to x in a nonlinear way. Plotting y by x yields this plot. If we take as our weak learner a model that interpolates between all points, we get a perfect prediction. So our interpolation model is unbiased. However, it is highly unlikely that this model would perform well on an independent test set. Therefore, it is a weak learner. In fact, generating a new vector x and new response vector y and our model that interpolates between all points shows a very different picture. So our interpolation model has low bias but high variance. However, if we repeat this procedure a large number of times and then average the results from our interpolated model, the fitted model, denoted by the points, recapitulates the true model, which is overlaid by the red dash curve. Classification trees are weak learners. That is, they can change dramatically when the learning set changes. Ideally, we would like to have multiple versions of our learning set drawn from the same distribution as our original sample. Unfortunately, this is usually impossible. However, we can imitate the process of having several samples drawn from the same distribution as our original data in order to form a more reliable predictor through bootstrapping. That is, a bootstrap learning set is taken from the original learning set and the classification method is applied. This process is repeated B times. Afterwards, the B predictors are used to form an aggregated predictor. A bootstrap resample is simply a random sample of the same sample size drawn with replacement from the original vector of data. This ideogram demonstrates that from our learning sample, we draw a bootstrap resample and derive a classification tree. This is repeated until we have B classification trees. The B classification trees are then averaged or aggregated to obtain a predicted class for each of the observations. The aggregated classifier is derived as follows. After fitting the Bth classification tree using the bootstrap resample, we obtain the predicted class for each observation. For observation I in class K, we let the indicator for the Bth bootstrap resample be equal to 1 if the predicted class is in class K, and 0 otherwise. Then the bagged estimate is obtained by summing the number of trees that predicted class K for observation I. The bagged predicted class is that class attaining the maximum. This is an example when B equals 5. For each bootstrap resample, we have a tree. For each tree, we drop observation I down the tree and get the predicted class. The indicator variables D are simply 0 or 1, representing the predicted class for observation I for the given tree. The bagged estimates are simply sums of these 0, 1 indicators over the B trees. And the predicted class is that which is the maximum bagged estimate. The IPRED-R package includes a bagging function. However, random forests is a more flexible method, so we will describe it next. Random forest is a simple extension to bagging. The primary difference is that instead of examining all p covariates at each node, a random sample of m of the p covariates is selected for split selection. The random selection reduces the correlation between the B trees. Remember, the average of uncorrelated unbiased models will be unbiased with reduced variance, so we want the B trees to be independent from one another. Sampling features for selecting the split at each node helps achieve uncorrelated tree structures. The remaining procedures are the same for building a classification tree. There are two natural byproducts from the random forest algorithm: out-of-bag estimates of error and variable importance measures. Out-of-bag estimates of error use those observations left out of the bootstrap resample to estimate error for the Bth tree. The probability that an observation is selected at least once and hence is included in a given bootstrap resample is 0.632. This means that approximately 1/3 of the observations are not in a given bootstrap resample, and so they are not part of the training set for that tree. We call these out-of-bag samples. Therefore, these out-of-bag samples form an independent test set for that tree, and they are used to calculate misclassification error. After fitting B trees, the B out-of-bag estimates are averaged to get an overall out-of-bag error estimate. Most often, we want not only to derive an accurate classifier, but also gain some insight regarding what predictor variables are important for the classification task. This is important because when there are a large number of predictors, it can be difficult to determine what predictors are important using traditional modeling methods. The out-of-bag observations can also be used in estimating variable importance measures. After predicting class membership for the out-of-bag observations, each predictor is permuted and the tree is used to predict class membership. The difference between the number of votes for the correct class and the number of votes for the correct class in the permuted data is taken. The average distance and accuracy of the out-of-bag observations versus permuted out-of-bag observations over the B trees is the variable importance measure for the Pth variable. The random forest R package includes the random forest function. Like rpart, the random forest function assesses the class of the response, and if it is numeric, a regression tree is fit. If it is a factor, a classification tree is fit. However, it does not include a method argument. So, to fit a classification tree to CHD, we first convert CHD to a factor. Thereafter, the random forest function is called, where CHD is modeled by all other variables in our HART data frame. If we are interested in variable importance measures, we should set the number of trees to a very large number. The default is 500. And we should also set the importance parameter equal to true. We see that the out-of-bag estimate of error is 31.4%. The variable importance plot is produced using this function. As you can see, age and tobacco use are the top important variables when using the mean decrease in accuracy. A similar variable importance measure is the mean decrease in Gini impurity as seen on the right. The random forest method is attractive since it can be used simultaneously to fit a classification model using all covariates, provide variable importance measures, and provide an estimate of generalization error. Therefore, random forest is attractive for use in settings where there are a large number of highly collinear covariates, such as is the case with high throughput gene expression data. Here are some further references.